Hello, welcome to Physics 2 last week of classes. Um, yeah, this is chapter 31. This is the end. Yay! So, this is going to be atomic physics. This is the branch between how physics becomes chemistry. Because really all chemistry is applied physics. And you can tell a chemist I said that. Before we get into it though, as is the last week of classes, let's just talk about where we're at and what's going on. So today being the 7th, I'm going to cover this chapter, or start this chapter. On the 9th, which is Wednesday, I will finish the notes for this chapter, and you have homework due from the previous chapter. On the 10th, your last lab is due. And also on the 10th, I am going to do a review where I'm going to go through last semester's final. It'll be 1 o'clock on Thursday. I will post that to YouTube after it is done. Friday will be practice problems. Sunday, the 13th, yes, Sunday will be your last homework, and your exam will be on the 14th, late in the evening. That's the general setup for how this is going to go towards the end. But that's the setup. Yeah, I'm going to finish lecturing, start this chapter today. I'll finish it Wednesday, Friday practice problems, and then this review on Thursday. I have written the final. I took the final, timed myself on the final, rewrote half the final, but that's where we're at. So, I'm going to get into this chapter though. This chapter called Atomic Physics is all about, well, atoms. Kind of makes sense. And atoms are the building block of all matter. It's what all things are made up of. And as I said before, this is the bridge between chemistry and physics. Now, I could just go and say, this is the atom and talk about the atom. But what I'm going to do is kind of do this on a historical perspective, talking about how the present model of the atom evolved to where it is now, or at least to what we think the atom is now. Keep in mind that the model of the atom is kind of a weird setup because we're still, I mean, it's so small, we're pretty sure what an atom looks like, but we're not 100%. So, I want to talk about the discoveries of the atom and the historical perspective of the model of the atom. The first person to define the atom and say the atom exists was a man named John Dalton. He was a school teacher, and way back in 1803, he said matter was not continuous, that all matter was made up of these pieces, that all matter, be it you, the desk, the air, everything, was made up of tiny, indivisible, indestructible particles. We later learned that the atom is divisible. You can break it, you can destroy it. We'll get back to that. But what he said is that the atom is the building block, that everything is made up of combinations of atoms. And all atoms of a particular element are perfectly identical. We now know that not to be true also. We'll come back to that. But when you have a certain element, all atoms are completely the same and have all the same properties. And the atoms of different elements can combine to form compounds. And when they do, compounds, that's what I have to do. Compounds just contain elements in whole number ratios. And so things like methane is CH4. That is 1 carbon, 4 hydrogen. But you could also have like butane, which is CH. Nope, I can't remember. Butane is also CH, but with different numbers. Let's do, for example, water is H2O. Hydrogen peroxide is H2O2, and so on. That you can take these atoms and rearrange to make different compounds. And people were like, cool, we got that. And for about 100 years, that was the model of the atom. Because, yeah, it was, let me just check the year again, 1803. Yep. 100 years later, in 1903, a new model of the atom was proposed by a man named J.J. Thompson. And this is going to start a real fun bit of people trying to one-up their teacher. That's the short version. So late 1800s, people saw that if you pass electricity through hydrogen gas, you can get positive and negatively charged particles. And what Thompson said is if that's true, that means we must be splitting the atom, that the atom must be made up of positive charged particles and negative charged particles. And that's what, when we shoot electricity through an atom, we're breaking it. And he proposed a model of the atom. Now, this is kind of impressive that even in 1903, he was able to accurately measure the mass of a proton and an electron. And he was able to work out that, yes, an atom is made up of two different types of particle. Note, only two is what he said. We'll get back to why that's wrong in a second. But that all atoms are made up of two types of particles, this heavy proton and this light electron. And he said that they could be charged as positive, as follows. That protons is a positively charged particle. Electrons are a negatively charged particle. And since he worked out the masses, and here I have the numbers show up, and he said since a proton is 1.67 times 10 to the negative 24 grams, an electron is 9.11 times 10 to the negative 28 grams, since it's so much bigger, what he said what a model atom is something, he said it was a lot like plum pudding, because I've never had plum pudding or seen it, but apparently this is what it looks like. It's also called the plum pudding model. But what he said is a proton is this big gelatinous goo with hard hunks floating around in them that are the electrons. And that was his model of the atom, that a proton is this big massive thing with just hunk O electron floating inside. And he accurately got the mass of a proton, mass of electron, and the charge of each of them, which is impressive. The downfall of his model of the atom, though, was, he had a student who decided to prove him wrong. Thompson had a guy working under him called Ernest Rutherford. Ernest Rutherford was raised a sheep herder, then went to Cambridge, and he got a PhD working for Thompson. And he said, no, this plum pudding model, bullshit. That's not what's happening. He said what's happening is that protons exist in the center of an atom, in what he called a nucleus. And the electrons orbit the nucleus at random radii. And he said not only is the nucleus protons, but there's a whole other thing that has yet to be discovered called an electron, called a neutron that is also in that nucleus. And that neutron, you have different number of neutrons in the same element, which going back to that whole idea that, that's not going to work what I'm about to do. Nope, I saw that coming. Going back to that idea that all atoms of an element are identical, he said that's not true either because you can have neutrons. Proving that wrong in Dalton. And for Thompson, just proving wrong the whole idea that it's a goo thing. Now, he actually had a pretty good reason for believing this was the case, for knowing that there was a nucleus with protons and neutrons and electrons orbiting around it. And actually, that basic idea still holds today, that an atom consists of a nucleus with protons and neutrons, and there are electrons further out. The difference is, once again, he said the electrons can orbit at any goddamn radius they want. They just were out there, and that was fine. Now, how he knew this is people had already kind of understood alpha particles. They didn't know what it was at the time, but they knew that if you had a radioactive source, it let off these things. They got alpha particles. They eventually learned that alpha particles were two neutrons and two protons stuck together. And he shot alpha particles at a very thin film of gold. And he found that most of the particles went straight through. Just didn't really hit anything. But he found some of them didn't. Some of them got scattered and bounced off at random angles. And while most of them are undeflected, some got deflected. And he said, okay, if my boss or ex-boss, he came this up after he stopped working for Thompson, because, if you're going to prove all your boss's findings wrong, you might as well stop working for him first and take all the credit. He said, if my boss's model of the atom was right, electrons are so goddamn small that we'll never hit an electron. And so it's just this big gelatinous goo, nothing should get deflected. All of the alpha particles should go through the gold. but some are getting deflected, which means there must be some hard hunk of something that we're deflecting off of. That there must be, a billiard ball in the middle we're bouncing off when we shoot that guy in. And that was the base of the nucleus. That this nucleus was a hard hunk that the alpha particles bounce off of. And that's why we sometimes saw deflection. And that was the model of the atom, that protons and neutrons are in the nucleus, and electrons orbit at various radii. And I mean, seems like a decent enough idea. Now, once again, this was in 1911, I want to say. 1911. That year is going to come up again in a second. So, any questions so far with all this?
No, going all right.
I'm actually going to write down the year 1911 because later on I'm going to make a reference to it, but I always forget what year and have to check. So, meanwhile, completely unrelated, seemingly. I thought to be completely unrelated. We'll get back to why it's not unrelated once I do the thing. Meanwhile, there's some other experiments people were doing. If you take a tube and you fill it with hydrogen gas, or really any gas, but we're going to talk about hydrogen mostly, and you excite it, aka put a shit ton of electricity in it, or if you want to go fancy, shoot it with lasers, or if you want to go the opposite order and the least fancy, set it on fire, it glows. And yeah, if you take hydrogen, excite it, which is once again electricity, fire, or something like that. For gas, you normally don't use fire. It's hard to burn a gas. For solids, you normally use fire. But if you excite it, it glows. And people found that if they looked at the light through a prism, that anytime you excited hydrogen, you got exact same lines at all times. That you saw a red line at 656 nanometers, a teal green line at 486 nanometers, and two violet lines at 410 and 434 respectively. With violet drawn as purple here, but really it's a dark, dark, dark blue. And people found that if you got a different gas, it would also have set lines. And that each gas had its own set of lines. And this was called the atomic spectra. I already said this. And that if you look, there we go. If you look at a gas excited, that all gas have a very set atomic spectra, sometimes called atomic fingerprints for this reason. And that all gases have lines at very set spots. That looked with the naked eye, you just see, for hydrogen, it's like a weird purplish color. It's a mixture of blue and red, so it looks kind of purplish. But yeah, you excite it, you get lines. And these lines are at a very set spot. Each gas has its own lines at its own spot. And they said, this works for most everyone. Helium looks like this, lithium looks like that, and so on. In fact, I don't think this is further in the notes, so I'm going to say it now. Helium is so named because it's named after Helios, Helios being the god of the sun. In Helios, Apollo is Greek. In Roman, the Roman god of the sun, couldn't remember if it was Greek or Roman for a second. Apollo is Greek, Helios is Roman, I think. If I'm wrong on that, don't judge me. I'm a physicist, not a mythology person. The reason it's so named after the god of the sun is helium was discovered on the sun before it was discovered on Earth. Because people looked at the emission spectra of the light from the sun and saw a line that they hadn't found in any other element. They're like, there must be another element on the sun that doesn't exist on Earth. Let's name it after the sun, or the god of the sun. Keep in mind, this is like the 1900s. They just like to name things after Roman gods at the time. And eventually helium was found on Earth. But it's a general idea. You excite something, it makes these lines. And people didn't really understand why, which is a cool thing. You get lines. Yay! But in 1885, and yes, I'm going back in time. So this is before the model of the atom that we had last. In 1885, a man named Johann Balmer found that you can mathematically find exactly where these lines in hydrogen exist, following the equation 1 over lambda, lambda being the wavelength, equals a constant times 1 over 2 squared minus 1 over n squared. Now, it seems weird that I'm saying 1 over 2 squared, not just 1 over 4. There's a reason for that. We'll come back to it. but I think he actually did put it as 1/4 minus 1/n². But he said you can find the wavelength, these lines in hydrogen. This line at what I say, like 660, 480, and I forget the other ones. They were on the other slide. 410, 434, 686, and 656. That you can find these exact lines by just plugging in RH as a constant, known as the Rydberg constant, which is 1.097 times 10 to the 7th inverse meters. And if you plug in n as an integer, you got these wavelengths using n equals 3, 4, 5, and 6 respectively.
Can you
And
adapt that equation to work with other elements?
no, and we'll get into why in a little bit.
All right.
We'll kind of get into why, but yep. A little bit after that, a different man named Lyman said, hey, if we get an ultraviolet camera and we look at the light in ultraviolet, your equation still works, only with ultraviolet, this 2, wait, that's not what I wanted. This 2, if you turn that 2 into a 1, it matches the line in ultraviolet. And then pretty soon after that, a man named Pashan said, hey, if you look in the infrared, there's more lines in the infrared. And if you replace that number 2 with the number 3, they explain the infrared lines. And so the equation changed. Things are not showing up in the right order here. So we're going to see what happens when I do this. There you go. That just showed up already. And people said, you know what? It's not the Bohr's equation. There's the Rydberg equation. Well, the Rydberg equation explains all of the lines. That there are lines emitted in the atomic spectra of hydrogen following this equation, where n is always bigger than m. And if m equals 1, that's the Pashan series. If m equals 2, that's the Bohr series. If m equals 3, that's the Lyman series, and so on. There's names for almost all of them. Where only the Bohr series is visible to the eye, but with an infrared or ultraviolet camera, depending, you can see these other lines, and it works. Okay? Now, meanwhile, this was understood. Well, this was understood in the way of people like, this equation works. And it was one of those, why does this equation work? And everyone went, I don't know, it fucking works. Don't question it. Just, it works. Which is always the worst answer to give to a physicist. And so people were like, okay, these equations work, cool. And then Rutherford was like, hey guys, this model of the atom works. And this one guy, his name was Niels Bohr, decided to look at both. And 2 years after Rutherford's model of the atom, Bohr looked at it, said, hold my beer, and decided to improve on it. Quite literally, Bohr is known for really liking beer. He had a pipeline going from his house to the Carlsberg Brewery, which was across the street. So he actually had a beer on faucet straight from a brewery. And Niels Bohr said, I can explain the atomic spectra by fixing Rutherford's model of the atom. And this is what he said. Well, first off, before he said anything, he made 4 assumptions. And this is one of those things in physics that he made 4 assumptions because if you make these assumptions, it works. And people are like, why can we make those assumptions? He's like, shh, 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 be quiet, it works. We'll get into proving these assumptions later. And the assumptions he made were as follows. 1, electrons move in a circular orbit around the proton due to Coulomb force. And basically, an electron is a negative charge, a proton has a positive charge, they're attracted. And if you give something some tangential velocity with the attractive force, it'll move in a circle. This goes back to physics 1, the same idea that like, if I spin this in a circle, it moves in a circle because tension keeps it on its path. It's the same idea, that we can say the Coulomb force equals ma, where a is just centripetal acceleration. He then said, only certain orbits are allowed, aka the radius. It's not any goddamn radius you want, like was said 2 years earlier, but only certain radiuses are allowed. And at those radiuses, no energy in the form of electromagnetic radiation is emitted. So the total energy remains the same. Now, normally, anytime something has acceleration, which is has centripetal acceleration, there is radiation of energy. But he said not at these radiuses. At these radiuses, it's fine. He then went with it and said each radius corresponds to an amount of energy. And any time an electron in the hydrogen atom goes from one radius to a different radius, a photon is emitted. And the energy of that photon equals the change in energy of the two radiuses. That if it goes from a radius further out to a radius further in, we can say the energy it had at the further radius minus the energy it has at the new radius, that's the energy of the photon emitted. He actually called the various radiuses energy levels, which I'll get to in a little bit, because he said each radius corresponds to a certain amount of energy. And so each radius is a level of energy or an energy level. And his fourth assumption, which I'm going to explain in more detail on the next slide, is that the circumference of the orbit, aka the circumference at each radius, must contain an integral number of de Broglie wavelengths. That the radius only can exist at exact radiuses because we have to match the de Broglie wavelength to how far around it goes. We good so far?
Yeah.
Okay. I want to explain why assumption 4 is the easiest. Well, assumption 1 is really easy to explain. Proton, electron, they attract each other. They move in a circle. There you go. Number 4 is actually one of the next easy one to explain. And number 4 actually kind of explains 2. Number 3 is conservation of energy. So let's explain number 4. And I am going to turn on my camera for a second. So de Broglie said electrons, I'm just going to cover this mismatch one for a second. De Broglie said electrons have a wavelength, the de Broglie wavelength. But this wave is moving in a circle. And so if this wave is moving in a circle, that's the same as if I tried to loop this around to make a circle. And for it to be continuous, the wave has to line up where it repeats and be a nice continuous all the way around. If I tried to line this up like so, and it doesn't line up, that's not going to be a continuous wave. But if I line this up so it matches, it has this radius. If I line it up further to find another spot where it matches, that's this radius. And that only certain radiuses are allowed because only certain radiuses can the wave function, like here it doesn't line up, can the wave function line up with itself? And it said that if we don't have an integer number of wavelengths based off the de Broglie wave, we get this mismatch. It would be an unstable radius or an unstable energy level. So let's run with these assumptions. The first assumption was Coulomb force equals ma, where ma here is going to be centripetal acceleration. So that means the Coulomb force, Ke, charge of one thing, charge of thing, radius squared equals ma. But a is centripetal acceleration, v squared over all. I'm making it negative mv squared over all because I'm just saying it's going to be in the negative direction. Well, if I take this equation and what did I do here? I just got rid of the f equals and I squared e. Negative e times e is just negative e squared. But from something we covered earlier, well, no, this is something we covered. Just a general idea. The kinetic energy, though, he found could be given as this. The logic from that is just rearranging this. Because what we did here is we're saying Ke squared all equals mev squared. If I take this and multiply both sides by a half and divide both sides by negative sign, the negative sign just cancels out, I get 1/2 mv squared equals ke squared over all times a half. And therefore, this equation says the kinetic energy must be ke squared over all. Make sense so far?
Mm-hmm.
Kind of skipped a step there. He said for potential energy, we know potential energy of a charged particle is ke q1 q2 over all. We covered that in like the second chapter. So the potential energy is negative ke e squared over all. But total energy is always kinetic plus potential. So total energy is ke squared over 2all minus ke squared over all. The negative sign because my potential energy is negative here, while the negative sign cancels out of my kinetic energy. And doing that math, that means the total energy is ke squared over 2all. Now his fourth assumption said only certain radiuses are allowed based off the wavelength. And that wavelength there, if you remember, was the de Broglie wavelength. It's an electron. And it kind of shows it here in this picture in the bottom right. I didn't really stress this one before, but that's the assumption 4 shown differently. We know de Broglie wavelength is h over mv because it's h over momentum. If I take that equation and let me just keep getting my tools out. If I took that equation and shove it into this equation, I can then say, okay, well, I'm going to multiply both sides by mv. I'm going to divide both sides by 2 pi. Just rearrange and say mv all equals n h over 2 pi. He didn't actually write it that way. He introduced the term h-bar, where h-bar is h over 2 pi. It ends up that h divided by 2 pi is so constant that people got sick of writing it down, and they just always wrote h-bar instead. H-bar is just understood to be h over 2 pi. This is physicists being lazy right there. So what we're going to do is we're going to take that and some of the stuff we had earlier. We're going to take this guy right here. And I'm going to use this to solve for v squared. I'm going to take my equation in the upper left and divide both sides by negative m. And I'm going to take my equation in the upper right and divide both sides by mo. Well, let's just stress so you know what I'm doing. This came from here, this came from there. I'll then square my equation on the right and say v squared equals v squared. I'm going to set these two equations equal to each other. So let's see. I will multiply both sides by mo. If I multiply both sides by mo, the ones on my left disappear and the ones on my right reduce. And if I solve this for all, I get this equation. And this says for a hydrogen atom, keep in mind this was only the hydrogen, because if not, we have that whole Coulomb thing is going to break down a little bit. I'll explain that a little bit. And this goes back to why the equation works for things not, if the equation works for things not hydrogen. But for a hydrogen atom, that's the radius. That the electrons can only orbit at certain allowed radiuses, because h-bar is a constant, the mass of an electron is a constant, Coulomb's constant is a constant, and the charge of an electron is a constant. And so we can only have rays at set radii that follow this equation. Now, of note, n equals 1 is known as the Bohr radius, often called a sub naught. And it's just the radius for the first energy level, where a sub naught is 0.0529 nanometers. And that means the radius of any other energy level, every other allowed radius in a hydrogen atom, is given as a naught n squared. Where once again, a naught is just that hunk. Okay, questions?
All
Any
right.
questions?
No. Actually, I think this is starting to get a little more familiar because I took a couple chemistry classes at my
Oh
previous
yeah.
college.
Oh, we'll go in chemistry. Okay, so that's the radius. Now, we also said each one of these radiuses corresponds to an energy, but earlier we said energy was negative ke e squared over 2r. So what I'm going to do is I'm going to take this radius that we just found, and I'm going to take it and plug it in right there, which becomes this mess. But all of that is constants. And if you plug that in, and I'm going to do something weird here. I'm not going to work in joules. I'm going to convert from joules to electron volts because that's the normal. If I plug all that in, I get this equation. That the energy is given as negative 13.6 eV over n squared. I would normally work in eV when doing these energy levels, but if you want, you can convert it to joules. And the lowest energy state, when n equals 1, is the ground state. And the energy, sorry, this is bothering me, the ground state. I didn't close my parentheses. And the ground state is just the energy at the first energy level. And if you plug in different values of n, you can find each other energy level. That n2 is negative 3.4 eV. And he said the highest energy level is going to be when n is infinity. But if n is infinity, this goes to 0. And what we're going to do is we're going to define infinitely far away as 0 energy. And as we get further in, the energy decreases, but we're going to say it goes more negative. That negative 13.6 is the lowest value, because negative 13.6 is less than negative 3.4 because we're going more negative. What this says is if we want to remove an electron from an atom, we need to have enough energy to overcome the energy it has there. So for example, to remove an electron from the ground state of hydrogen, that takes 13.6 electron volts. This is known as the ionization energy. And he said this right here would tell you what the value for each radius is and how much energy an electron has at each of these radii. Now, his third assumption was any time an electron moved from one energy level to another, it emitted a photon. But we're saying anytime an electron is in an energy level, it has a certain amount of energy. A certain amount of energy given as negative mk e k squared e to the fourth over 2 h bar squared, or just simplified negative 13.6 ev over n squared. Well, let's go with this. That any time an electron goes from one energy to a level, it emits a photon. Well, we're saying the change in energy is hf. And if I divide both sides by h, that means the frequency is E1 minus, or EI minus EF over H. Which, once again, E goes by that whole mess, so that's the same as this equation right here, since they both depended on n squared. Now, most of the time, though, people don't deal with frequency, they deal with wavelength. But keep in mind that frequency is c over wavelength. And if I plug that f in for this f here, I can eventually rearrange. I did a step of rearranging where I divided both sides by c to get this equation here. And if you do the math right there, MEKE squared e to the fourth 4 pi c h bar cubed, you get the Rydberg constant. This is the Rydberg equation. This explains the wavelength for each line. And here's the thing. When the Rydberg constant was first derived, the logic was, hey guys, this number works. They didn't do the math and they didn't do the physics and say why. They just did the math and said, if it's this number, it matches. And the Bohr model derived out the Rydberg constant from fundamental quantities, showing that this equation matched. And that the reason we have these set emission lines is because it's changing energy. And when an electron relaxes from one energy state to another, it releases a photon. The wavelength or the frequency of that photon is the energy of that photon is based off the change in energy. If it goes from negative 1.5 eV to negative 3.4 eV, that change in energy, that's the energy of the photon. And as we know from previous, the energy of a photon is based off the frequency, which is what we view as what color is it. And so it all works out. Now, Bohr described his model as a potential well. And he said if you have a well, a real life well, if you want to lift the bucket out of a well, it takes energy. And just like this, if you want to take an electron out of his potential well, it takes an energy. And he said the top is zero energy. And so since we're going down in energy when you go down, just like potential energy, you go down in energy when you go down, since it's beneath the zero state, that's why they're all negative values. And he said the lowest state, the one that the electrons want to be in, things want to have as little energy as possible. And so everyone wants to be in a spot with the minimum amount of energy. And he called that the ground state, which would be n equals 1 for hydrogen. And said anything higher is an excited state. And that if you excited an electron, aka put electricity into it, it'll jump to a higher level. And this matches before that how we got this emission spectrum was by exciting the hydrogen gas. And he said when we put the electricity, the electrons jump to a higher energy level. And they don't like being at that high energy level. You see, because we have these multiple energy levels, the electrons can move between them. At room temperature, everyone's going to be in the ground state, lowest possible energy. But when they are excited, they will jump to an excited state. And what's going to happen is the electron will go, looking at my GIF here, or not GIF, just my picture, from maybe E1 to E2, because you excited it. Once an electron is excited, it doesn't want to be excited. Once you excite an electron, it says, fuck, I don't want to be here, I'm going home, and we'll go right back to where it started. But the thing is, anytime it goes back to where it started, you added energy to push it up, and then once it's up, it on its own, spontaneously, this is called spontaneous emission, went back to where it started. But when it went back to where it started, it lost energy. And whenever it loses energy, it's going to make a photon. That photon is going to have energy equal to the change in energy levels. Now, of note, if I go from the fifth energy state to the first energy state, one electron, one photon. If I go from the second to the first, one electron, one photon. Every single time one electron relaxes, you get one photon. 5 electrons relax, you get 5 photons. The size of the jump has no effect on how many photons are emitted, which we view how many photons as how bright it is. But the size, how the change in energy level will say what color it is. That if something is going to drop from one energy level to another, every time it drops an energy level, it'll make a photon. That photon of a set wavelength. Because conservation energy says it has to be the same. And here's the thing. Things don't always go immediately to the ground state. If you watch my GIF, 1, 2, 3, 4, I excite it to the fourth energy level. It's relaxing from 4 to 3, then 3 to 2, then 2 to 1, kind of in steps. It can jump however order you want. Maybe it'll go fight from 5 to 1. Maybe it'll go from 5 to 2. Maybe it'll go from 5 to 3. They can relax at any sort of spots. And actually, that Bohr series is anytime something relaxes from the higher energy level to the second. That if you excite electrons from the first energy level in hydrogen, some will drop back down to the first, causing the Lyman series, but some will relax down to the second, which would be the Bohr series you see when you put it through a spectrum. That is not hydrogen. There's an orange line here. I need to fix that because hydrogen does not have a line there. Sorry, that's a mistake. And he said the emission spectrum of any other element, be it helium, argon, neon, anything, is just following the same logic. And he didn't mathematically have an answer to the equation for it. This goes back to the earlier question. There is no equation like the Rydberg equation to explain this for other elements. But for any other elements, the same idea. Those energy levels, the electrons get excited, they go to a higher energy level, they then drop down, and as they drop, they release a photon. Photon of energy equal to the change in energies. And when you excite different gases, you get different colors Because why you get different colors is you're looking at a collection of different emission spectra. And as you look at a collection of different emission spectra, it's going to be based off where the energy levels are in that element, where it's different depending on the element. Questions?
Nope. Still going.
Okay. Now, okay, that's why. This has been all talking about exciting with electricity. You don't have to excite with electricity. If you this is fireworks. When you have like fireworks, the different colors is actually this idea that everything when you burn it will burn a different color. The reason why is when you set something on fire, you're exciting the electrons. When the electrons relax, they shoot out photons. Where they relax to would depend on the material. So, with my last little bit of time, let's do a problem. Okay, photon is emitted when an electron and hydrogen atom jumps from n equals 3 to n equals 2. Calculate the energy, wavelength, and frequency of the photon. So, the energy at each state is just given as this equation. And so the energy of the photon would just be the change in energy of the states, right? This whole E initial minus E final equals HF. So the energy of the photon would just be the difference of the energy levels. Now, if I'm going from n equals 3 to n equals 2, that means n initial is 3, n final is 2. And so the energy of the photon is just negative 13.6 eV over 3 squared minus negative 13.6 eV over 2 squared, or negative 13.6 over 9 minus negative 13.6 over 4. I can do that math, and there you go. The energy of the photon is 1.89 eV. That's the energy of a photon. We're saying change in energy is HF, so that means that energy of the photon that has to equal HF. So if I want to get the frequency of the photon, I set that equal to HF. And I can divide both sides by H. But this energy is in EV and H is in joules. So I'm going to have to do a quick conversion. 18.9 EV, 1 EV is 1.6 times 10 negative 19 joules. So if the energy is 1.89 EV, that's equal to 3.022 times 10 to the negative 19 joules. But the frequency would just be that energy once I convert it over H. That's the frequency of that photon. You want the wavelength? Wavelength is speed of light over frequency. Easy enough to do. But this model was good. This model worked. Whoa, 1913? This model didn't last very long. You've probably been taught this is what an atom looks like. You have probably been taught that an atom has a nucleus with protons and neutrons and radius orbiting at set radii. This is commonly taught to people in middle school and such, because it's a simple way to look at the atom. But here's the thing. The Bohr model isn't quite right. It works for hydrogen and works for hydrogen-like atoms, but has never been solved for any other atom. What I mean is it works and only works if you have only one electron. It works if you have one proton, one electron. It can also work in something like, let's say you have a helium atom. Helium has 2 protons, 2 electrons. If you take a helium atom and rip off one electron, it'll have 2 protons, 1 electron. It'll work for that. You just replace E squared with ZE squared, where Z is the number of protons. Changing the equations as follows. But it doesn't work if you have multiple electrons. It only works if you have only one electron. And anytime you have more electrons, it all breaks down. And there's a very simple reason for this. The basis of all this was it was all based off Coulomb force. That if I have my nucleus and an electron, let's just go bigger. I say there's a force here, and the sum of forces equals ma. So the sum of forces equals mv squared over r, and that's the basis. But let's say I have 2 electrons. And let's say at a moment in time, my second electron is here. Well, there's a Coulomb force pushing this forward, but there's also a Coulomb force pushing this way. And as this moves, this second electron, they're not always going to be the direct ratio of each other. That maybe at some other point in time, this electron, when it hits here, this guy's here, meaning the first electron's that way. And this equation right there will stay true, but this piece of that becomes complicated as all fuck. Because it's going to be that it's always perpetually changing which direction. That if you have more than one electron, and that electron is changing location relative to the second electron, and this is just for 2. If you go up in the periodic table, like let's say I want to deal with oxygen. Oxygen has 8 electrons at various energy levels. And so if I have a second energy level out here with more electrons, I'm going to have to say, okay, this electron, to solve this one, we have to say the first from the proton, the first from this electron, this electron, this electron, this electron, this electron, that could be moving at any spot. But on top of that, I have to do the same for each of the other electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now it's oxygen, now it has 8. And it becomes mathematically impossibly complex and can't be solved. And so, going back to the earlier question, does that equation work? Does the Bohr equation work for other elements? Only if it only has 1 electron. It can work with helium that you remove an electron, or it can work with lithium that you remove 2 electrons. Where I'm just going across the periodic table. Helium with 1 helium has 2 electrons, 2 protons. So if I say we remove 1 electron, that's 1 electron. Lithium is 3 electrons. So if we remove 2, we have 1. But anything more than that, we can't handle the math because we have to deal with too many Coulomb forces. And that's not the only issue with the Bohr model. You see, he looked at hydrogen because the 1 electron made life easy. But he could not solve it for anything more. And this was one of his biggest issues with the model, that he admitted that he had problems with his own model of the atom because it only worked for hydrogen. And also he made some assumptions, right? I started with 4 assumptions. One of them was that there's no radiating of energy. One of them was that these quantized states. And the quantized states was because literally his reason for the quantized states was this thing, and like taking something a wave and wrapping it around in a circle. Which when you're trying to do quantum physics, saying if I wrap the paper around in the circle, the lines line up, is a pretty bullshit way of trying to prove something. And so this model of the atom also didn't stay held for very long. A new model of the atom came out in 1926, disproving it. And this new model of the atom, we've already covered it. It's the Schrödinger equation. The Schrödinger equation, which I showed you last chapter, and I talked about the wave function of a particle. What he said is, this is how an atom actually exists. That if you were to solve this problem and solve this equation, that you could get the wave function, the psi, the trident-looking symbol. And if you find that trident-looking symbol and square it, it'll give you the location, it'll give you the probability of the location of a particle at a given moment. And what he said is electrons do not orbit at set radii. However, there are set radii where they are more likely to be. And what he said is electrons, you have no goddamn idea where they are. This matches the Heisenberg uncertainty principle. You can't know exactly where. If you follow the Bohr model, it says it's at this radii with this energy. If we know its energy, we know its momentum. And the Heisenberg uncertainty principle says if we know its momentum, we don't know the location, and vice versa. So therefore, that Bohr model breaks the Heisenberg uncertainty principle. And so what he said is this is just a probability that the Bohr radius of 0.053 nanometers, that is where the electron is most likely to be. And when you solve the Schrödinger equation, you can find where the most likely place is. And that for more energy levels, you can figure out where it's most likely to be. Now, this is called the cloud model or the quantum mechanical model. And it's called the cloud model sometimes because it's not saying a set radii. This picture at the bottom is the cloud model for hydrogen in its ground state. It's just a pink glow. Wherever it's darker, it's where it's more likely to be. And what it says is it doesn't tell you where the electron is, it tells you where it probably is. You can't know for sure where. And that the electrons don't orbit at set radii, but they're just around there. But most of the time are at that radius. Now, people teach the Bohr model as true because it's a really good approximation. It's easier to visualize. And mathematically, the Bohr model works perfectly for hydrogen. But it's only part of the story. It's really a lot more complicated. And moving on with that, the Schrodinger model has also only been solved for hydrogen. That the equation is too complicated that no one's ever been able to solve it for anything past hydrogen. But when you solve it, which is something you can do, I had to do it in grad school, you'll get all of Bohr's models numbers working out the same. And so we use Bohr model as an approximation. And that's why you are normally told that electrons orbit at set radii. They don't, but it's a good way to look at it. Any questions?
Nope. Still following.
I did go over, I apologize. I get excited sometimes talking quantum physics. So we're going to stop there. Wednesday will be the last day of new material, with Friday being example problems. That's the setup. Have a good day.